electrons, which are trapped. And these are experiments which are actually done here locally at Michigan State by the group of Johannes Polanen, who many of you may know. And together with a postdoc who has actually moved to a company which Johannes has started in Chicago. So I'm going to jump a little bit between slides and whiteboard. Feel free to interrupt me. These are the people which have been involved. So Nias is was a former postdoc of Johannes, and there are people from quantum chemistry, and then there are also some people from Oslo, and there are two experimentalists as well. Marianne is actually a postdoc in Zurich at the ETH, and she's working with point defects, which is another hot candidate system for making quantum gates and circuits and so on. She's excellent. There are many different motivations for looking at quantum computing. So all of us have been struggling with the many-body problems, and we know that many-body problems, we have the dimensionality curse. And there's quite some interest in using quantum computers and quantum computing algorithms, in particular due to the massive parallelization which you can do, which quantum mechanics offers, which is one of the big advantages. For us of doing many-body physics for ages, we've been trying all kinds of tricks to reduce the dimensionality. It can be smarter basis functions, resummation of specific correlations, machine learning algorithms, etc., etc. So here it's more what this talk actually is about. Is at the end, it's going to be a little bit about how you can run simulations of systems, but it's going to be more into what you might call quantum engineering. So this is us recycling many-body methods to actually design quantum circuits and quantum gates. So you will recognize a lot of traditional many-body physics, which we then use to simulate the systems, and then find the optimal parameters which can then be used in an experimental setup. So you could think of theory and experiment being together. You could almost call this loosely for quantum twins, just to play on digital twins, in the sense that you have a software which you use to find the optimal parameters, which then can be used in experiment, and then experiment can feed back to theory. I put up a lot of references here. So if people are interested, there are several textbooks and also useful references. There is a recent one colloquium on advances in automation of quantum dots. So these are the systems we're going to look at. Johannes Polanen has been writing together with many other people, amongst these Martin Savage, who many of you know. They've been writing an article on, or the white paper, position paper, on practical quantum advantage towards practical quantum advantage. And there are quite some initiatives on actually running quantum simulations experimentally and theoretically. And in a sense, this talk is this kind of mix between theory and experiment, where you use theory to guide the experimental setup. And if you're interested, just shoot me an email. There is also a paper on the Lipkin model, which many of us know from nuclear physics. And it is a simulation. This is actually just a theoretical simulation. If I get some time at the end, I will show you how we can use the setup of Johannes Polanen to actually prepare an experimental setup for studying the Lipkin model. And in this case, it's going to be the Lipkin model of a 3x3 matrix, which we are going to diagonalize. That's an impressive thing. But it's going to be something which we can rewrite in terms of 2 qubits only. And the system today is actually a 2-qubit realization with quantum dots. These things have been here for many, many years. Actually, I was very much inspired by a paper by Hjorth-Jensen and Loss, which came in '97. In that case, they were looking more at spin systems, but the system was actually a quantum dot. And there have been tons of papers after that. but it's only now where people have been able to trap the electrons in small areas. And this is done, for instance, by people like Johannes Pollan. So the technological advance which has taken place recently is something which allows us to do what I'm presenting today. I should also say that what's happened in the last 30 years with being able to trap down to single particles in small areas. So like when I started to study physics, which actually now is 40 years ago. So when Jilin said we had a young speaker today, thank you, that saved my day. But then back 40 years ago, I mean, most of the experiments were done on ensembles of particles. And then with the ion traps and pending traps, et cetera, you have the capability now to actually isolate few particles and test basic properties of quantum mechanics. And that makes it very interesting. And this Ryan LaRose, he begins as a assistant professor at Michigan State. He did his PhD last year, and he was hired at Michigan State at the CMSE. And everybody knows Jelena, who was actually the first FRIB theory fellow, and then got a permanent position at Western Michigan. So there are many requirements. You want the things to be scalable. You want qubits to be entangled. You want a reliable initializations. You want to have a set of universal gates from which you want to run the calculations with. You want to have a coherence time, which is longer than the gate operation time, et cetera, et cetera. So there are many requirements. And what we're actually doing is actually to develop a theoretical framework where we simulate the system with experimental parameters and see whether this can be realized or not. There are many candidate systems. Some of these links you can click on. The system which we are going to look at is quantum dots, which you can think of electrons trapped in small areas. And this is a technology which they have been developing. Point defects in semiconductors, there's also activity here, Michigan State in the School of Engineering, but there are also many other places where they actually look at it. Now, the electrons on superfluid, again, if you have access to the slides here, so for those of you online, I can actually put that into the chat, so you can access the links if you want to. There is a very nice video which Johannes Pollan made for the APS meeting. And what they actually deal with is a Coulomb-driven entanglement. And there's a systematic investigation of controlled generation of entanglement between two trapped electrons. And I'm coming a little bit back to how you realize this experimentally. Let me just move on a little bit. The methods, for those of you, the many-body aficionados, this is time-dependent many-body physics. And one of the methods which has been used in the atomic and molecular physics is has an acronym which is called multi-configuration time-dependent Hartree-Fock. So that's the kind of acronym which is used. So time-dependent full configuration interaction theory. You can have time-dependent copper cluster theory, time-dependent density functional theory, et cetera, et cetera. So these are some of the basic tools. And actually here, it's full configuration interaction theory, which is the simplest many-body method we can think of. If you can diagonalize, you have the answer. So entanglement is actually this fundamental characteristics that distinguishes quantum systems and which allows us also to have this massive parallelization. And the entanglement of two qubits is something which has been demonstrated across many types of platforms, superconducting circuits, trapped ions, semiconductor quantum dots, et cetera, et cetera. So this is the, I'm going to skip some of the slides here. But I wanted to bring up a warm-up problem. And I'm going to switch over to the whiteboard and prepare you for the what is the main problem we are facing. So let me see if I can get it up here properly. So the thing we are going to look at now is two electrons in two traps. So you could think of a system like this. So what we are doing now is that Johannes and his collaborators, they are able to set up electric fields on top of a layer of superfluid helium, and they can trap single electrons. And their claim is that they can localize these single electrons. They know that they are in a specific well. So the kind of system you could think of now, if you look at these wells, you will have a set of discrete states. Yeah. So the background there is that it actually gives you almost no influence from the environment. So you cool it down to almost 0 Kelvin. If you look at so this is another thing I wanted to say. Everything which has to do with quantum computing, all the systems, they are complicated many-body systems. So if you think of nuclear physics, the complication we often have is that we couple to the continuum. So that's something which increases the size of the dimensionality for an isolated system like a nucleus. If you think of these solid state systems, there you have an environment which is actually a great source for noise. And sometimes you have thermal excitations which actually ruin your computational basis. So let me now bring in these ideas here. So if you look at these states, all the devices which have been made, they try to find specific states which can be used as computational basis states. So that means that if you think now of this as system A and this as system B, you could now think of the lowest lying state as something which represents bit 1 and the next one as bit 0. So I'm going to put an A here and an A here. And then you have a 0 here and a 1 here. But we know that these wells, they have a huge amount of states. And if you have a harmonic oscillator, you have an infinity of bound states. Else you have scattering states, you have the bound states, etc., etc. So what you want now is to build up many-body states as a tensor product between these computational states. And when you're going to do measurements in the system, you would typically use Pauli matrices. So you transform your Hamiltonian in strings of Pauli matrices. And you know that the state of bit 0, which is actually something you would represent as a spinor 1, 0. This state here is an eigenstate of the sigma C matrix. And the same with the bit 1 with negative eigenvalue. So when you make a measurement, you're projecting out something. So then you would like to project out whether you have the qubit in or the state in system A or in system B. And when the systems are entangled, you know that if you make a measurement on system A, you know exactly what happens in system B if you follow the rules of quantum mechanics. Okay? Just feel free to ask questions here. But this, if you see this, this is the computational basis. So when you look after an experimental system or a system in semiconductor physics like point effects, you're often looking after systems which have two well-defined levels, which you then can adopt as your computational basis states. So that means that if you now trap many electrons in many such small traps, you can have many qubits, which you can build up a simulation on. And the fact that you have 2 to the n with n electrons, for instance, that gives you an extreme amount of degrees of freedom in order to describe many particle systems. So the whole thing now is that everything you deal with is to hope that the environment does not spoil your computational basis. So this is the kind of overarching thing. Then there's another thing which comes in. And you're probably familiar with density matrices and von Neumann entropy and things like that. So what you often are looking after are states, computational basis states for, let's say, a 2-particle system, which has an avoided level crossing. So the avoided level crossing is the one which actually maximizes the subsystem entanglement when you calculate the density matrix. So but the kind of overarching message is actually what you have here. And this is irrespective of whether you're using ion traps, whether you're using superconducting qubits, you're always looking after some low-lying states which you can use as computational basis states. Clearly, if you heat up the system, you have thermal excitations, and that ruins your computational basis. Yeah. So this is a many-body system. So what I will show you, actually, the talk is how you design the system so that you can treat A and B as almost independent systems. So that, yes. You actually anticipated everything I'm going to say, Alex. So the whole setup is actually you tuning these electron traps with the electric fields, which they can set up in the lab, so that you can treat these systems A and B as almost independent systems, because then you can operate with a laser or any other kind of device you have to excite it without affecting the other one. So this is the, actually, this is a very interesting question for research. So we theoretically, we can simulate these systems so that we have, if you look at the wells here, and I will show you in the calculations that if you look at the wells, if you make the threshold high enough, there is a small likelihood that you will have tunneling. So ideally, you would like to have one electron in each trap, because when you then, you know that that trap is located in a specific place. And what Johannes and Nias have done recently is actually to trap one single electron. And they claim that within the uncertainty principle, you can localize the electron. What you don't know is what happens if you have a contamination, right? Because you could trap another electron. So theoretically, you can actually simulate that and find out what kind of conditions can make you avoid having more than one electron. So that's a nice thing of having a theoretical simulation tool. Yeah. No, you can actually, Johannes, if you say beyond fermions, he won't talk to you because he has a company. And that's actually some of the technologies they're trying out, because here you also rely on the transistors, the CMOS transistors. And when you cool things down to a very low temperature, it's very difficult to scale it up. But you can run simulations on the system. You can actually set up the experimental setup and simulate a specific quantum system. But it's most likely this system here, according to him, is not something which will be of commercial interest. Yeah, there was a question in the back there. My hearing is pretty bad actually, and I have this AirPods in here because I. Oh, you have to. I mean, theoretically, you can run the calculation, right? And then you have experimental measures by, like, computing the one-body density, which you then can check when you run because when you run the experiment, you run it many times, and that means that the you would then have measures for whether your one-body density represents one particle or not. So theoretically, you can run it, and then you can benchmark the tomography you do experimentally with theory. And I guess that's the only way, because the quantities we are going to talk about, like the density matrix, they are not quantities you measure, right? So entanglement is not an observable. Okay, so I'm going to go back to the slides. So this was more meant to set up the basics here. And I see that there's a question in the chat. Okay, so I'm going to repeat the question on the Zoom. So the question was actually to Carlo, is whether, how can we know that how the electron is entangled with an electron far away? And one of the things you can do then is typically to calculate things like the density matrix and check that that gives you what you would expect for having just one single particle in that. And then you experimentally, you would have to devise how to do that. Okay, so let me just move on a little bit. And I wanted to show you one of the things which becomes important. So I'm taking this problem as a kind of warm-up problem first. So it's a 2x2 matrix, very exciting. And it has the two basis states. So it has an unperturbed Hamiltonian, and then we have a interaction which we can tune. And this is actually what we are going to do in the paper here. We're actually going to tune the single particle potentials so that we can optimize entanglement. And what you can get in these systems is something which is called avoided level crossing. And when experimentalists are looking after these candidate systems for computational basis states, the 0 and 1 states, you're often looking at systems which are close to what we normally call an avoided level crossing. So in this specific case, I have just designed, so this is the Hamiltonian. And if I get some time later, I will show you how you can actually set up gates to simulate that Hamiltonian with the setup of Johannes, if we get some time. And you can actually rewrite this 2x2 matrix in terms of sigma z and sigma x matrices. That's pretty trivial to see, actually. And that's normally what is done. Actually, when you're simulating systems, you would transform the Hamiltonian from, let's say, second quantization to a representations in terms of sigma x, sigma y, and sigma c matrices. Because when you do the measurements, you're doing the measurements on your computational basis, which is this bit 0 and bit 1 basis. And the sigma c matrix has these basis states as eigenstates. So when you project out, you perform a measurement, you project out either bit 0 or bit 1. And that's why you typically rewrite the Hamiltonian in terms of sigma z matrices. You can rewrite a sigma x matrix in terms of a sigma c matrix, and the same with a sigma y. So this is something which I will not deal with, actually. But this system here, when you run it, what you would see is something like this, as a strength of the interaction. So at the interaction strength equal to 0, this state is given purely by the lowest state, the 0 state, and the other one is given by the 1 state. And then you have an avoided level crossing, which then gives you the change of state. So here the state will be dominated now by the state up here. And at the end here, it will have a stronger and stronger influence of that one. So this level crossing is also something which gives you a much larger entropy, and then von Neumann entropy, and an entangled state for a subsystem, which we're going to see now. So the avoided crossing plays a central role in quantum simulations, and it results from the coherent transfer of the population between the states. And when you say you have a coherent state, that means that the quantumness and entanglement are preserved, and the system follows our equation of motion. In real experiment, it's not that easy because you have thermal excitations which ruin your computational basis. The thing which is nice actually with the system we have here, and this is very much thanks to Mark Dickman, whom everybody knows here. And Mark has actually developed this theory of superfluid helium in contact with these type of systems. And he has shown that the influence from the environment on these systems is very small at low temperatures. So actually very much of what Johannes and other people have realized is due to the theory work of Mark Dickman. So when you do quantum technologies, these different systems are coupled. So you can enable various quantum state transfers and manipulations. And experimentally, this avoided crossing of the energy level is one of the first features to look for, since it manifests the signature of preservation of quantumness. So I'm not going to remind you of density matrices, but I'm just going to state it here. So you have an orthogonal basis, and this would be the probability is actually the eigenvalue of the density matrix, and that's linked with the orthonormal basis which you've chosen. And this is the quantity which we typically use. Oh, I should just cancel this one here. So the 2-qubit system. So this is back to the drawing I made. So this will be the system A and B. So I have 2 qubits, 0 and 1, and then I do the tensor product, and then I can define a new orthonormal basis. I could have taken linear combinations of these. I could have taken a linear combination of 0, 0 and 1, 1, as you see here. And that would be a so-called Bell state. That would be an entangled state. But I could use these as my basis. So these are the basis states. So that means, and you won't be surprised, this is going to be a 4x4 matrix to diagonalize. And in my case, I'm just rewriting things in terms of like we normally do in nuclear physics. We have an unperturbed Hamiltonian, which we can solve, and this unperturbed Hamiltonian has these states as eigenstates. And then you can add an interaction term, which is now given by some parameters. And then you have the tensor product of sigma x and sigma z matrices. And that gives you this Hamiltonian here. And then you diagonalize. The thing here is that you get this same kind of avoided level crossing. And you can define the ground state as a state you use to calculate the density matrix. So in quantum terminology, this is a pure state because you know the state. You know that the system is actually in a combination between the state. It's still entangled, but it's a pure state because you know it. When you diagonalize, you have the coefficients here. But then you can trace out the subsystem density matrices, because then you want to figure out how entangled a subsystem is with the other subsystem. And that means you would trace out here, and then you can calculate as a measure, you can use what's normally called the von Neumann entropy. So this is the classical one, the classical entropy. And you know that this one is something you can rewrite in terms of the eigenvalues of the density matrix. So that's, I guess that's pretty standard quantum mechanics. And then we calculate that one for the subsystem. And then you will see when you do that, so if I run it, you will see if I do the ground state, you have an avoided crossing here. And then I trace out for one of the subsystems, it's irrespective which, because theoretically they have to be the same. And now you see that the entropy starts at 0 here, which is because you have only one state. You are in the 0-0 state. And then as you gradually start mixing in, you see now that you have an increase in entropy. And this is something which hits in when you have the avoided level crossing. So experimentally, what many people do actually is to tune the parameters so that you can have a two-level system which exhibits this kind of avoided level crossing. I'm going back to the slides, and now I wanted to show you the kind of calculations we have done. And so I'm going to skip that one. This is a little bit about this. Actually, if you want to read more, when you have access to the slide, there's a great article by Mark Dickman, a recent one in PRB. So the system now is a system where you can now tune different electric fields, and you can produce an effective potential which looks like this from above. So it's a lateral potential. So in a sense, you can omit the degrees of freedom in one of the directions. It's a two-dimensional system. And it doesn't look like a harmonic oscillator, but what we have done now is to take these parameters here, which are set up experimentally. So these parameters from alpha 1 to alpha 7, these are the parameters which we are given. And then we use many-body theory together with optimization algorithms to find the parameters which optimize entanglement for a two-electron system. So you could now think of an electron being localized here. So Johannes and company, they've been able to localize one electron now. They have not localized two. So the nice thing with the theory calculations is that because they know the parameters, they know how to do it experimentally. But you have a huge amount of parameters and you don't know which are the optimal ones. And it takes time to etch the circuits. So that means that you would like to have a kind of guidance, which are the optimal parameters. And this is what we can provide theoretically. So that's essentially the project we've been dealing with since COVID. So they have a range of frequencies and these constants here, which they can deal with experimentally. So that's within the range of what they can achieve locally in the lab. Did that answer the question? Yeah. Oh, the x-axis is actually, the x-axis is the distance between the two wells here, actually. So you could think of having an effective trapping potential here, and this is in micrometers. So that's the distance, the typical distance. It should be down here. Yeah, here you can see the x-axis. So this is the distance between the two centra. And what we are doing is actually to make a fit. So we don't have an analytical expression for the potential, but we have a fit. And that enters the numerical machinery. Yeah. So essentially what we are solving is an effective potential, the trap potential you see here, which comes as a parameterized potential. And we just feed that into our programs. And then we diagonalize the one-body problem. We create a one-body basis. And then with that, we create a two-body basis. And then we diagonalize the two-body basis. That's essentially what we are doing here. So so this is it's a double well created by, so they have a set of electrodes. And these are things where, if you ask me in more details, I can only repeat what's on the slides, because that's what Johannes gave me. I don't have that in-depth knowledge of the semiconductor technology they're using, sorry. And what we did then is actually to investigate a model which consists of two electrons confined to one-dimensional external potential. And then we used exact diagonalization to solve the two-body problem. And we have done this in several ways. So, yeah. Yeah.
So I'm the funnel. So you have the technical field and then you have some kind of like field.
Yeah.
That's not from the field, the helium that comes from the.
Yeah. Yeah.
What is the role of the helium?
So the helium is actually the environment which the system lives in, and it's cooled down to almost 0 Kelvin. And that couples weakly to the electron system. So that means that the environment, you can see this as almost two isolated electrons. So the role of the helium here, as Mark has showed, is that it perturbs weakly, very weakly, the electron system. Because if you look at the superconducting qubit system, that's a complicated many-body problem where you have the environment. As I said, when we do nuclear physics, we have the continuum to deal with, which complicates life for us. Whereas in solid state physics, you have a complicated environment. So so basically what we're doing now is to have a Coulomb interaction, and then we have this potential, which is given by these electric fields. So a parameterized potential. So this is normally parameterized by some finite element method, and then it's fed into us, and we have the parameters we can play around with in an optimization process. So this is not advanced machine learning, actually, it's just a plain optimization of the problem. And the potential now, since we're dealing in one dimension, we actually have a screening or shielding constant. You can reduce this to one-dimensional problem, but what we have done recently is actually to tailor everything for calculations in 2 and 3 dimensions as well. But in this work is done with a one-dimensional Coulomb potential. Yeah. Oh, this parameter A? Oh, so this will contain the standard constants which you have in front of the Coulomb interaction. So that will be your permittivity in vacuum, 4 pi, the charge, and so on. Oh no, this just becomes a parameter we play around with. Yeah.
So these roundings kind of come down to the 2.
Yeah.
Then actually, they're supposed to change the underlying.
Yeah.
How do you know that form?
We don't have, you would have to have a calculation of, let's say, a screening parameter in order to get that pattern. So we haven't done that. We just fixed it to a small constant in order to avoid the divergences. Yeah.
So is it like a dielectric system?
Yeah, yeah, could be. Yeah, that's right.
What is the transport of that?
I wouldn't know. I wouldn't know. We would have to ask Mark then. He's the expert on that. I couldn't tell you, Bill. I don't have that in-depth knowledge of the system. So what we did, we built a basis with a DVR basis with a sinc function, and we did the left and the right wells as 2 subsystems. And the other thing we did, and this is something I have to say a little bit about. We've done several calculations before we actually settled on what we thought was the easiest one, or the one which still gave a pretty fair reproduction. So the first thing we did was to treat these as fermions and start with an anti-symmetrized two-body wave function. And we had the spin degrees of freedom, et cetera, et cetera. So we actually tested that instead of taking the standard anti-symmetrization, what we did at the end was actually to take a Hartree basis. So we didn't do a Hartree-Fock calculation, but we just took a product of two single particle states because we treat these as distinguishable objects. But we checked that against a calculation where we treated them as indistinguishable particles. And the thing is that the height of the well, what separates the two potential wells, is so high that we found there was basically no tunneling and no affection for the states which we want to have as computational basis states. So think back to that image I showed you, where we have computational basis states, which are the low-lying states in the potential well. So we checked that with an FCI. So we have many, many states. And with an FCI calculation, the states which we are interested in are the 4 lowest lying two-body states. And they are not affected by electrons which are in the high excited states. And there is basically no tunneling effect for the low-lying states. So when we run the calculation either with a Hartree basis or a full anti-symmetrized two-body wave function, we got essentially the same results. And that simplifies things. It simplifies things because in this quantum computing language, so what we're ending up with is actually this approximation for the ground state. And these orbitals are orthonormalized. And then with that, you can calculate the von Neumann entropy by tracing out the density matrix for the subsystem. The system you have, and I don't know how familiar you are with this Schmidt decomposition. So what happens then when you perform a Schmidt decomposition, if you look at the upper equation, you perform a singular value decomposition of your density or your wave function, two-body wave function. And that's something which can then be rewritten out in terms of a product of two wave functions. And these two wave functions correspond then to the left and the right system. And they have an almost one-to-one overlap with the Hartree states, which we obtain by performing a Hartree calculation on each subsystem. So the singular values then are just the values you get by performing a singular value decomposition. And there's something in quantum computing which is called the Schmidt decomposition, which means that you can actually then treat the two systems as two separate systems. So in this particular case, this is actually what happens. And then we can calculate the von Neumann entropy. And if we now look at the calculations, I'm going to show you results for two types of results. One, where we don't have a avoided level crossing. And two, where we have cases of avoided level crossing. And then we're going to look at what happens with the entropy for the subsystems. So the first case is something you will see in the figures here. So let me just first show you. This will be the typical basis function you get for one of the wells. And these are the energies, which are also energies which would be typically achieved experimental. So this would be the transition energies. And these are the one body densities. This is the depth of the well in mega electron volts for the left well. And this is, in this specific case, you see you have a one body density for the ground state. This would be the bit 0 case. This would be the bit 1. And these are all the other excited states. So when you are setting up a two-body simulation basis in order to perform quantum gate operations, you would like to use only these lowest lying states in order to make a two-body state. So you will see a similar level density for the other well. So these are the single particle states in each well. Then you can now see the interesting case. So this is the product of the single particle waves for each well. So this is the non-interacting case, and this is the interacting case. And this lambda is a parameter which we use to tune the trapping potential. The Coulomb interaction is kept fixed, and the distance between the two wells is kept fixed, but we can tune the electrodes which are used in the setup of the traps. So this parameter is a parameter which we can tune, and obviously we have a case here where we have basically no level crossing. And if you go back to that simple 4x4 matrix, you saw also that the entropy of the subsystem was basically 0. And we are now going to look at what happens when we have a level crossing here, but we also have a triple level crossing. So these states, which you can see, you can probably see the numbers. So we also have a problem with some of the states actually coming lower than what we want. So this would be a state which you can identify as 1, 0. So this is the first excited state. So the ground state is down here. The ground state will be bit 0, 0. This is bit 1, 0. This is bit 0, 1. This is 2, 0, but this would be actually the 1, 1 state. So we have a state which comes below here. And at this level crossing, this is where, so we would actually like to have as a computational basis the ground state and the state 1, which is now 1, 0, state 2, which is 0, 1, and then the state 4 is actually 1, 1. So we have a kind of intruder situation in here. So when we are dealing with this 2-qubit system, we would ideally like to have 4 computational basis states. And this is some kind of scenario you actually have to live with when you're looking after these states, which you construct a computational basis with. So you have the single well computational basis, and you have the double well computational basis, which is a 2-body basis. And that's the one you would use to simulate a 2-qubit system. So you can see now, this is a case when you don't have a level crossing. So this will be the 1-body densities. So this is 0 and 0. This will be 1 and 0. This is 0 and 1. But this is 1, 1. And you would actually like to have that lower. But we've been tuning these parameters so that actually comes higher up. But as long as these states are well separated and you can do experiments, you know the frequency differences, you can still pick 4 states and use that as your computational basis. So what we are saying here is that you see roughly which frequency are relevant, and they can be realized experimentally when you're now operating on the different systems. Now, the coefficients, if you just skip that one, this actually, what we did was actually to calculate the natural orbitals. And you see now that the ground state, which is 0, has basically both states in 0, 0. And you can see that. There's no mixing with anything else. You go to the state 1, 0, which is actually this one and that one. And then you see you have a mixture of 1 and 0. And then there is something here which comes in. So there's all, these states are not pure. Remember now, these are many body states. So we will always have some noise which kicks in. So ideally, we want these to be separate and distinguishable systems. But here you can actually quantify how much comes in from unwanted configurations. So this was in, yeah. Say it again, yeah, yeah. This one, yeah, 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 yeah. It's a triple crossing, yeah, yeah, yeah. So at that point, say it again. I haven't thought of that, Vitek. That's a good question. I haven't thought of that. Yeah. Oh yeah, yeah. No, that's true. That's true. Yeah. Say again. Yeah, that just goes. Yeah, yeah. So actually, you have a level crossing between the blue one, the purple one and the green one. That's where you have the level crossing. Yeah. 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 Exactly. Yeah. 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 Actually, that's a good point. It's exactly as you had in this Lipkin model case. Yeah. Where one states remain just flat. Yeah. 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 Okay. That's a good point. Actually, this data are pretty fresh. Then if you go to the interacting case, now the case with the where we have the, let me just increase the fonts a little bit here. So this is a system now where you have, these are the two states which you saw here, these two states to the left, and then you have the other ones to the right. And this is about the structure of the states when you have this triple crossing. And you see now that you get an admixture of the states. So this would be the normal, the natural orbitals or the natural coefficients for these states. And you see now that you have a higher mixing from the different coefficients. So 0, 1, 2 would be this bits, the states 0, 1, 2 in the left well, and then similarly for the right well as well. So you see you get a larger degree of mixing, whereas one of the states, actually so the ground state stays the same, as you can see, is not very much affected, as expected. So with the ground state, that consists only of 0, 0. Whereas the other excited states, so this would be, if you look at, so if I can guide your eye here, so this would be the second state, which we have here, and this is the third state. You have a smaller mixture, but then you go to the 3 states up here, where you have the level crossing, so they are almost at the same energy level. And there you see you have actually from the structure which you see here, you can actually do some analysis. So I haven't done that yet because these results are pretty new. Then if you go to this level crossing, you can then calculate the entropy. So the ground state stays flat, stays at 0 here. It's like the Netherlands seen from the sea. Actually, you don't see the Netherlands from the sea because it's below sea level. Sorry, I couldn't resist. Perhaps that's why the Dutch people are the tallest people in the world. Anyway, you can see now S1 and S2, they're actually practically on top of each other. And you see that for this parameter lambda, this is where you have the double crossing. And this actually shows you really a increase in the von Neumann entropy and as a measure of entanglement. And you have a similar one for the parameter lambda here when you crossed 1 for the 3 next excited states. So these are things which you can then use in studies of entanglement and when you want to perform computations. So where we are now is essentially here. So this is actually what we have done till now to demonstrate that you can set up experimental parameters to have entanglement due to the Coulomb interaction. And by tuning these electric fields so that Johannes and Nias and his collaborators can go back to the lab and set up the experimental setup and perhaps even realize the systems. And what we are planning to do is actually add time dependence to this and look at the time evolution of entangled states and again find the optimal setup to perhaps run some simulations. And ideally, I think they think that within 1 year, they may have realized this 2-qubit system. That's the experimental timeline. And these are the plans for the future. And there's quite a lot of activity on running this type of simulations. And my hobby horse here is obviously to set up a nuclear Hamiltonian and try to devise a quantum simulations, which can be run experimentally and compare that with theory simulations. That's a kind of long-term goal which I have. And the starting case is actually going to be the Lipkin model with spin 1, which translates into a 3x3 matrix. So that's the, it's not something you will impress people with on a party on a Friday evening or whatever. But still, to realize that one with quantum simulations is something which I think is very interesting. And for us nuclear physicists with lots of experience in time-dependent many-body physics, this is actually what happened, because Johannes and we just met over a cup of coffee, and he said he was dealing with trapping the electrons in quantum dots. And I've had this interest since '97. And then I asked him, why don't you trap 1 and perhaps 2? And then it led to this collaboration. This is just what happens when you randomly meet a colleague at Sparty and then have a small chat, and then this happens. Okay, guys, I have more, but I'm going to stop here actually. Sorry. Yeah. So we've been, this is an excellent question. So the results you saw is after fine-tunings of the anharmonicities, and we could never get rid of that intruder states. So we've been tuning and tuning and tuning, and we can't get rid of it. So that's a very good question, actually. So the wells are anharmonic, actually. That's a very important thing. So we, in the optimization code, we were not able to find a case where we could get rid of that one. But the frequencies are so well separated that they know how to run experiments. Yeah, exactly. We were not able to, so that's actually something we want to investigate more, actually. That's a very good question. Thanks. Yeah. Yeah, the thing is that that's a good question, but the thing is that this is just electromagnetism, right? So I think yeah, I'm not sure actually. I wouldn't know that. I wouldn't know the answer to that. Yeah.
The energy scale goes down.
Yeah, it does actually. So maybe it's beyond reach of the frequencies they can measure in the lab. I would know Wolfiards, the specs there. I can ask both Mark Dickman and Johannes. Because it's all electromagnetic forces, right? But probably the well would have to be much deeper. Yeah.
What does the experimental data actually look like? What are the observations?
Oh, they haven't run experiments. They haven't realized this yet. So this is theory calculations where we try to find the optimal parameters for the electric fields. And then they want to realize it afterwards. So they haven't run an experiment. They've been able now recently to trap 1 electron. But that hasn't been published yet. So so there's no experiment here yet. Yeah. Oh, so clearly, I mean, actually Dean and we are supervising a student who run these calculations of specific expectation values on the IBM machines. And he could see that when there were many people running, then they had to recalibrate because he got the totally wrong expectation value. So if you were supposed to get a 50-50 case, you got 48, 52 or things like that. And it didn't give you the statistical expectation value which you wanted. And then they had to recalibrate when they recalibrate, because you have many people which use the machine, and then you have thermal excitations, and that messes up your computational basis. So that's the big issue actually. So finding a computational basis which you can deal with in a larger temperature range without you losing the computational basis. That's one of the big issues. So I didn't. Oh, what kind of traps? No, these are just electric fields which are set up and trap the electrons. Well, yeah, the temperature is close to, it's close to 0 Kelvin. It's just a few nanokelvins actually. Yeah, yeah. No, that's the. So if you act with a laser and so on, then you can really mess up things. Absolutely. But the thing is that there's a lot of momentum in actually performing basic research in these directions. And I think that's what makes it interesting. And there's a lot of interesting many-body physics for us doing nuclear physics. And this is actually a case where we've just been using the standard shell model, what we call it in nuclear physics, or configuration interaction theory. Yeah.
For the audience here, this is about particular example.
Yeah.
And the relevance of quantum
yeah.
Yeah. But in general,
oh yeah, yeah. So if you think of ion traps, it's not so different, except that there you also have the Coulomb interaction between ions, and but there you also have a much more complicated many-body system. Yeah, I would guess that. I would guess that. They have realized 2 qubit operations with many of these setups.
So in manual, so the whole thing has component part.
Yeah.
And then peripherals will have mechanical part.
Yeah.
So it would be like a simulation of it.
Yeah. Yeah. That's what I said. I mean, this is the interesting thing from a many-body theory is actually that this is a complicated many-body system. Yeah, but you have the environment. If you take away the environment, then it's only 2 electrons.
So using the real thing for simulation,
yeah. But that's much more complicated.
Don't have. Question from online.
Okay.